Hola, amigos. I'm joined here today on the Earth Awakening Discord for Celestial Theodolite Update number 4. Now, Mike's been busy with his dog rescue, so we don't have any new measurements. So we're just going to be doing a quick recap of what the Celestial Theodolite is. We're going to be going over the most recent measurements that were done really quick, and then any questions, comments that have been put forward since the time that the last one has been. We'll do a little update there, touch base with. All right. So to start us off with the basic premise of the celestial theodolite, what is it? Well, if we look over here at vantage point 1, if we have a little lad on the ground with a theodolite and he looks over at that mountain and he takes an angle to it, it's going to measure about 2 degrees and 19 arc minutes. And the question then becomes, is that elevation physically valid, or is it optical? Is there optical compression that's causing that, or is that the physical elevation due to Earth curvature? Right? So there's two different predictions that could be made using plane trigonometry. We can make a prediction on whether or not the elevation angle of that mountain is true with respect to that angle. Now we're going to have to introduce a secondary factor though to do this, and that's going to be a star. So we'll get to that here in a second. But first, we calculate out our angle for a flat Earth using just our elevation, the distance to the mountain, and that will give us the angle, the plane trigonometry angle off of that. Now for the globe, you just determine how much of the mountain at that distance would be obscured due to curvature, and that'll be your missing amount. So that we'll have two different relative elevations to our distance here that we're going to calculate. Then we can go into stellarium. We can go to the peak of this mountain here, and we could set the angle to be what we calculated for a flat Earth. And any stars that intersect at that angle, we write down the time, and then we go and wait. And when that time comes around, if that star gets intersected at that time, that means that the relative angle there that we derived is the physical angle of the mountain. That is the physical elevation of that mountain because it is there blocking the star as we no longer see the star. Now, a lot of people will say, well, what about refraction? How about refraction? What about refraction? Well, if an object is no longer visible, it's no longer refracted. So that's the point of this. That's the basis of when we take the time to get our measurement to confirm. So if the Earth is a globe, the premise is pretty simple. The stars will get occluded at a later time because the star has to get lower into the horizon to get lower to that physical elevation that's tilted away from us relative to our distance. Then on a flat Earth, it'll be occluded earlier because the physical peak is actually higher than what it optically looks like. Because at our distance there, it would look like it's 2 degrees and 19 arc minutes, but in fact, the star is being blocked at a time that corresponds to 2 degrees and 31 arc minutes. That was the basic premise and first measurement that was done using Pike's Peak from a distance away from 50.7 kilometers. Now, since then, more mountains have been used at different distances, and we have obviously different stars that correspond with that. All right, and each one of these is showing the plane trig or flat Earth prediction is the correct prediction, and no times have shown globular prediction, except for one, which I'm sure we'll get into here in a little bit. Oops, there we go. So that's our ether cause logo there. All right, so here's the most recent measurements here. Now, 1 second. So there was a what was it? There was a correction made to the way that Mike calculates and does his estimations here. So the big difference here from the previous celestial theodolite prezzies is this here where it says calculates the altitude of the peak, which is equal to altitude of the observer plus the distance to the peak times the tangent of the true elevation angle that the star was occluded at. And that will give you the actual elevation angle, or I'm sorry, that will give you the actual elevation. Okay, so that's what he's using, just plain trig to derive based off of the angle that it gets occluded at, what the actual elevation would be. And then he has columns here for the spreadsheet, starting with what the altitude predicted by the globe's statistics that are given to us. So like most of the time when you go to Wikipedia and you type in, what is the peak of this mountain, you can get the stats there. So he's comparing that, and we're looking for the difference in the predictions for flat Earth versus globe when we do the plane trig versus the trig to subtract what the missing difference would be for the globe. And what we have here are these two columns that show that the true elevation of the mountain peak is for Pike's Peak all averaged out. It comes out to be about 44 plus or minus uh, what they tell us, plus 44 feet. So the globe difference there comes out to be 246 plus or minus 7 feet. And this is how much should be missing, right? Due to globe drop at this distance, there should be 200 feet missing. So the globe difference there, 246, is what it comes out to be. In other words, the timing isn't matching what the globe predicts. The globe predicts this is physically lower than you. So we're looking at measurement after measurement of the timings not matched. Now, some of these you'll see are negative values. Now, what this comes out to be is that it came out slightly lower than what the values that were, the official values that were given, but still lower than, or still higher than what the globe would predict. So we have all the differences there. And that's all the measurements that we have so far. And we can get into questions, comments, and concerns.
I've got a question, if I may.
Mm-hmm.
Did you figure out any resolution on the 2,000 extra feet on the new updated time lapse from Dr. Heffron on Greenhorn Mountain?
I sure did. I'll read you what he emailed me. All right. He says, what Jesse appears to be doing is wrong, is what I mentioned to him in my response in April 8th at 7:28 p.m., which I blind copied into you. Specifically, Greenhorn Mountain, the small plateau directly above the letters R, E, E, and H of the words Greenhorn in your video, is not occluding any of the stars in his video. All of his data appears to be referring to stars occluded to the range between Greenhorn Mountain and North Peak, not visible beyond the right edge of the screen. Also, Jesse is trying to steer the comparison to complex analysis rather than the simple planar trig, which is the altitude of the peak is equal to altitude of the observer plus the distance to the peak times the tangent of the elevation of the occlusion angle.
So
it seems to be an error in your analysis, and you're just kind of still presenting it or whatever. That's what he's saying.
Well, but
and what did I talk to you about it?
What exactly did I do wrong?
Did you email him about it? Well, you're looking at a place where stars aren't being occluded, I guess, and then attributing the time to that. I don't know.
Did you double check any of this?
I watched the video earlier. Didn't see any stars there.
Which video? The one I put at 22 after?
Video?
The one at 22 after?
At 22 after. Yes.
You didn't see any stars getting included in that video?
At the section where it says EENH or what?
Well, stars get occluded all along that ridge line, that skyline, and I did the timings on a whole bunch of them, and every one of them was about giving indications about 2,000 feet too high. So
I don't know what mountain peaks those are, because the Greenhorn one that Mike said is in the bottom left-hand side. So I don't know what ranges you're even doing. The error is in your analysis, as he said. You're looking at a different peak, he said.
What? He called it Greenhorn. It's his time lapse. He called it Greenhorn.
And the section of Greenhorn is between the letters that I read off. What you're referring to, he said, is a different peak.
Well,
he said he talked to you about this on the 8th.
Is there an occlusion by that peak? Is that what you're saying? And you just kind of keep saying it, even though there isn't been?
We're not going to keep going in circles here. So, is there anything else?
All I can say is check it for yourself. I checked it very carefully on Stellarium, and the star patterns matched up very well for the mountain he claimed it to be. And do your own calculations. Tell me what elevation you get. That's all I can say. I got about 2,000 feet for the six of them that I tried. 2,000 feet extra.
Okay.
I do have an unrelated question if no one else wants to turn.
Go ahead. What do you got?
So my first question is, and I just posted the the diagram. If the light were curving between the star and the observer, would that change the occlusion time? I mean, if the star is setting or rising or whatever,
is the star visible or not at the time? That's all that matters, Jesse. That's the answer to the question. Is the star still visible or not?
Yeah.
But wouldn't it change the occlusion time, or would it not? Are you saying it would not change the occlusion
But would
time?
it be visible at a specific time, and then is that the time that it was measured, or no?
Well, I'm saying that refraction could change if refraction was curving the path of the light between the star and the observer, that could actually cause it to be visible after it had set below the straight line geometrical occlusion point. So at that point, it would still be visible longer than it would have been, and still visible and still being refracted, and the occlusion time would thus be delayed, right?
Luckily, we're going with when the star is no longer there, and we don't care at all. We only care when the star isn't there. Doesn't matter.
So are you saying that the light curving would not change the occlusion time as the star set?
I'm saying the only time that matters is when the time the star isn't there. That's it. It's very simple.
Well, the time that it transitions from being there to not being there, that is the occlusion time, right?
Obviously.
Okay, so it stands to reason that if the light ray was following a curved path, that could change the occlusion time, right?
The only time you get is when the time it's not there, Jesse. So it doesn't matter. Whenever it's not there is only what matters. Do you like when you said all right, next, do you have another question?
Well, I do. It goes on the basis of the assumption that stellarium gives the true angle with atmosphere turned off. Why does it give it only sometimes, right?
What?
Well, is it an assumption of the Heffron method that stellarium always gives the true physical angle to a star with atmosphere turned off, given the correct date and time and observer location?
Yeah, when you turn off refraction, it's just referencing where it would be like in the nautical almanac.
Okay, so the problem is you could have one person at the top of Pike's Peak with his laptop and stellarium, and another person at the same moment in time at Heffron's house with his laptop and everything, and they both turn off atmosphere, and these two instances of stellarium are giving different angles at the same point in time to the same star. So how do you know which one's the true angle if they're not both the true angle, are they?
Ooh, great question. We know when the star isn't there, that's the true angle. So if the star isn't there, that corresponds to the angle that we calculated, then that's the true angle. That's the beauty of this, and that's why we don't have to. That's the whole purpose of this, was we never told stellarium where we were at.
Right, stellarium doesn't know the observer location, only the location of the mountaintop, Jesse. Right, so wherever you see it from, right, doesn't matter because stellarium still gives you the same output. That's why.
That's our premise.
But stellarium with atmosphere turned off is how we ultimately know the true physical elevation angle to the mountain peak, right? And to the star, right?
Nope.
Not to the mountain peak.
Nobody cares about what you just said.
No, and that would give different predictions at different locations. The whole purpose of this is for that unified triangle at the same time with respect to the geometric positions, the raw trig positions of these places, and the raw uncorrected location of that star. Right, that's the purpose of this. So when you introduce what you're doing, it's not relevant. You're going to have different values at different places. That's not the purpose of this.
I'm going to take the argument somewhere where it's not.
Yeah, dude, talk about, but remember when the iteration of the argument was moving the observer to where he isn't or whatever? Like, I'm going to move the arguments where it's not. It's a great one, Beast. But yeah, if there's any other questions or comments, concerns.
I have a comment. Can we, one of the things Jesse has always taken this from kind of an analyzing the data point of view, and it strikes me that it's worth just looking at the method itself from a purely practical standpoint. And one of the best ways to see that the method itself doesn't work is to apply it to a small nearby peak at sea level, as I've done in a thing. Let me post it again.
Post that PDF one more time about a small peak that's like a mile away, then it's not analogous and it's retarded.
Yeah, no, hold on, one second. The sky moves at 4 arcsec or one's what is it? Every 1 second it moves 4 arcseconds, the sky, right? And you're trying to measure an occlusion timing difference of 8 inches. That's an improper use. You're not going to yield a discernible difference there. Nice try. You didn't debunk anything. What you're proposing is a misapplication of the celestial theodolite. And if you could actually measure a timing difference to that magnitude,
I don't know what you're talking about, actually.
What is it? That difference where it would be 4 arcseconds over 8 inches. I mean, dude, that's preposterous, right? But let's say you could do that, right? Let's say you could. you would measure the timing difference, right? So your issue here is the limitation of mechanics to get the difference of 8 inches. That's not, oh, the celestial theodolite doesn't work at 1 mile. Works great
I
over all
don't
these
really
distances
understand.
where we have all these measurements that falsify the globe using plane trigonometry, John.
No, I honestly don't know what you were even talking about just now. Can we look at the thing that I just posted in the? It looks like you've looked at it, but I don't know what you mean by 8 inches. And there's all sorts of things I really don't understand about what you're saying here. I think we're talking about two different things somehow.
Like the smaller the distance, right? The harder it is to differentiate between globe and flat. That's it.
Right.
The sky literally moves a greater distance in 1 second, than what you're talking about for 8 inches.
I'm talking about.
That's why your analysis is invalid, and what you're doing is retarded. You want to go around and parade this 1 mile thing like you've debunked the celestial theodolite. You're sad.
Okay. Could I maybe just
here every week to remind everyone?
That's fine. Okay. I'd like to go through it, but I can see that you're resistant, so that's fine.
That's been Daza. That's been our premise the entire time. Yes.
You have to have it.
I'm really not sure what you're objecting to. You're looking at a small nearby peak, and I took the example of a peak that's 1 kilometer away and 1 degree of elevation, as both globe and flat Earth would agree, because it's so close that.
Well, then it's not useful. We're trying to figure out what is more accurate.
So it is useful, and I can explain why, as I do here. In that case, we both agree that the peak will be seen at 1 degree. Refraction is not an issue. We're going to see the peak at 1 degree. It's going to be at 1 degree. All of that, right? So the only issue is the fact that, as Stellarium will report, that standard refraction.
If anyone else has any questions, comments,
this is really okay. I get it. You really aren't interested in hearing this, and I can understand why.
Didn't you just say that there's no difference between flat and globe at 1 mile away?
Dude, the difference is 8 inches.
Here's the difference.
Optically, you could argue there's no difference, but there's an 8 inch difference. That's the difference that
Can I finish, or am I not allowed to finish?
That's what you're trying to measure a difference between using something that's moving.
That's all right. I know, but I just want everybody to appreciate the fact that Alan has no
misapplication
interest
of the tool, right?
Nobody cares,
right? Like suppose you have a wrench, right, and it opens up a certain amount, right? So you can only grip a nut that's a certain size, right? If you encounter a nut that's too small, are you going to go, the wrench is broken, the wrench is broken, duh! No, that would be retarded. So sit the fuck down, John.
He left.
The whole point is to say it as slowly as possible so I could try and trigger a response to make it against that, because otherwise I have no position. That's such a clear...
Just for the audience, though.
Does anyone else want to try to break the celestial theodolite? Right.
The point is to tell the difference. Right?
Exactly.
So we pick big, long observations, and the longer the better, the more distinction. So he's like, you know what I could do, guys, is to find a really short, shallow observation where the difference is negligible, and then I can say the whole thing is invalid. And that's all he had to say, but he'll take 10 minutes to say it in the most smarmy way he possibly could.
Yep. Yeah.
But in general, what he's trying to do is that you should be able to repeat this at many different locations with many different things and come up with a broad set of observations around the timing that you get for the predicted refraction-free angles, and see how it fits everywhere, right? Not just this one location.
It's not one location. It's 1, 2, 3, 4, 5, 6 mountains with different, let's see, 7, 9, 12, 15, 23, 28 separate observations. So
yeah, but I don't know, is it all from the same place, Shane, or has it moved around?
Have emailed me that they've done it, but because it's at their house, or near it, they don't want to reveal their location or whatever. But I do have some more things coming or whatever. People are out there are out there doing this. So I recommend we get some Southern Hemisphere brothers. Here's a position that Dr. Bennett took that was really, pretty much the most honest position you could take is saying that, at this place, right, at Mike's location, it just happens to be super flat there for some reason. And you would have to go and do this at other locations, across the world. So if we get some more lads across I know, right? But to be generous, right? So if we get some more lads, especially some Southern Hemi lads, would be nice.
Dude, it's funny because in the triangle, the first survey they ever did when they were doing Kansas and stuff, they had to write down, it looks remarkably flat, right? We're trying to comport it to a geoid and make it sphere, but boy, it looks flat to every one of our instruments. They had to note that. I remember reading that. Yeah.
Well, according to these guys, it shouldn't work good. Your thing should fall apart in the southern hemisphere because they claim like southern hemispheric refraction because there's like twilight's longer or something. Remember that whole twilight thing? Dusk
Vaguely.
is longer, and they claim like
Ooh.
extra refraction in the south because there's more water or something. Like they got reasons for it at that.
I don't
So
think
your thing
so.
should. What's up?
I don't think that's right, is it, Jeremy? That there's no special treatment of the southern hemisphere, particularly in stellarium.
That was what Zanuck had for why there was extra twilight in the south. I mean, if you got some other reason why there'd be more twilight in the south, let's hear it.
No, I don't know about the twilight. I'm just thinking
Yeah,
about this,
Zanuck
this
does, and he
observation
claimed
here.
Zanuck does, and he claimed it's refraction based.
I wonder if southern occlusion times would be longer based on longer twilight and dusk. That's an interesting observation. It probably would change with the seasons too then.
Unfortunately, all of my observation points faced east, so I'd have to look at rise times, which is not ideal. And I don't really have I need a telescope with a camera to do it.
Either way, what Alan was trying to say about Dr. Bennett was that to prove that it's not just an anomaly in Mike's location, if you get it done in multiple locations and prove without a doubt that it's not just an anomaly, that's the most fair rebuttal to it, is what he's saying, which I agree.
Yeah, I thought that was a good one, right? I was like,
Yeah.
So maybe it's only Kansas and around Dr. Heffron's house that are the flat areas on the Earth, and that you have to do it at different, like at any place but there to confirm sphericity. It's an interesting position.
Flat or level, Alan? Shane, sorry. Like the Bolivian salt flats, right? They're very level, but they ain't flat.
Well,
Why would
you know,
think?
the guys who measured it also measured the flatness by the timing of a Venus transit. So, you know, who knows, right?
Yeah, well, we've done. There's more modern measurements of the flatness. I know that for Bolivian salt flates, they've got a high resolution GPS study.
Yeah, that references the Venus transit timing. I know, I'm familiar with it.
Yeah,
dog.
and a spherical datum.
Your premise is my conclusion, dog.
GPS measurement.
No, mate. It's measuring the lat long, dude. It's the same fucking thing as always. Surprise.
Even in ECEF, they need a thing to call the surface, right? So they adhere it to a spherical curving surface from the datum.
You can measure the surface independently in ECF, Alan. I don't want to hijack your thing, but yeah.
Well, we're getting far off the celestial theodolite again.
Yeah.
Do you have any
that's why the
rebuttals to
celestial
it?
theodolite confuses me, right? Because I know that there are other measurements that clearly show the surface is spherical. The other thing that'd be really cool with the theodolite would be to get somebody on the mountain.
Here's the thing, though. They don't, though, right? The GPS uses timing corrections to comport it to the coordinate system, so you wouldn't know the difference anyway, right? What we have here, what should unconfuse you, right, is you have your oculars and a watch, and you're just seeing when you don't see a star anymore, and with some plain trig. That's about the most unconfusing thing possible.
It's kind of ironic.
Please, GPS time has nothing to do with things in the sky, bro. It's atomic clock synchronization. Atomic clocks are synchronized by cesium vibrations. It has nothing to do with the shape of the Earth, my man.
Yeah, but the thing is, though.
Yeah, but what?
The GPS.
Yeah, but what?
Alan, chill.
Nah, man, this is so dog shit. We have a plain trig measurement here that's not referencing anything that's already pre-cooked, and he's confused.
So how can you measure the shape of the Earth from one point? That's the other thing that confuses me here, right? Based on the timing.
I hope you find clarity.
You don't have any angle measurements as such, right? You're just doing the timing based on stellarium's prediction and published altitudes.
You don't have any angle measurements.
Yeah, none of the angles physically measured, right, actually line up with any.
All right, 1 second, Dazzle. Before we continue, does anyone else have any questions?
I would like to go over a specific one if we could when we have time. To check my math.
I have a question.
I just remembered we don't. What's your question, Shane?
Is the suspect guilty or is he not guilty?
Oh, right, that's a great question.
Put him for the analogy with a security camera on top of the mountain, make it a building, right? And there's a dude committing a crime. And if he's there at the time, then he's guilty. And if he's there at any other time, he's not guilty, right? Super easy. No wiggling out of it. No trying to make it about something else. Is the suspect guilty or not guilty?
Like I said, neither one's guilty. The flat Earth suspect was 2,000 feet from the crime.
There's one suspect. There's no multiple realities, timelines, alternate universes, none of that shit.
And it's a false dichotomy to say just because one suspect is not guilty that the other is guilty.
It was committed at the one time, and he was
it's
there.
A mutually exclusive outcome. No hypothesis. Like, what do you do? All right, man.
A binary choice.
It's been real, lads. It's been a slice. I'm going to go ahead and close out. Gio, thank you for being a wonderful host.
Alan, I'm still waiting for the Andromeda Paradox. That's right up your alley.
How was that?
Because it's like it's like the train thing with the two train stations, kind of like that.
Oh, by the way, Alan, I checked my email, and Dr. Heffron did email me on the 8th, but he didn't say anything about the 2,000 foot stuff. All he talked about was why the horizon line had gone up, and he explained it's because he'd moved the telescope because the flash started up, and he moved the telescope to get the flash out of the viewfinder, or out of the view.
He didn't email you on, one second, let me pull it back up.
He emailed me on the 8th of last month, having nothing to do with the 2,000 feet, and he emailed me on the 31st of March, responding to my email about his first 2 measurements of greenhorn, but that was really poor seeing conditions, and I told him he had misidentified his 2 stars, and he wrote back and basically said no, he didn't misidentify the 2 stars. But that was before he had released to me, or I had gotten a copy of his improved Greenhorn Mountain video, so he couldn't have been possibly responding to that.
Interesting. All right. Well, I will send you a DM on Telegram of what he sent me.
Thank you. Oh, sounds like I just got it.
Got all giddy.
But I do hope you check out some of those occlusion times and use his method to find out how high the mountains truly are. Because I think you can agree that with your prior statement on the Flat Earth Fridays the other night that the mountains were just 2,000 feet higher than published probably is unlikely because of how many airplanes would be running into them.
Right. Well, we will have to get back to you on that. Seems to be that he's saying that mountain peak or whatever isn't the one that isn't the right one or whatever. So I don't know. 1 second. Yep. Okay. Yeah, we'll do.
So the people who don't understand what John was trying to do, right? So what he's trying to do is pick the smallest measurement observation he can below the threshold where it becomes distinguishable between either model, and then saying that the whole process is null and void. The counter, right, would be if I took the spherical excess data, which I have, found the smallest distance between the two, and found measurements below 180 degrees, thus declaring their measurements of legit flatness would invalidate the entire process, right? Because I found a single measurement of flatness in the spherical excess data, then therefore any excess over that threshold is null and void. The whole process is silly. That's how retarded that is. Anyway.
It's the correct approach, right? Try it in other geometries, other locations, see what you get.
No, that wasn't a response to what Shane just said. I don't know who were you talking to me or something.
No, it kind of was.
Yeah. It's standard measurement practice, right? You try, or anytime you have a theory like this, you try and repeat it in alternative locations with different geometries under different.
Yeah, but that's
Not
what
with
you're
what-
implying.
See what happens, right?
What you're
Not with
implying
what
is
Shane
that.
said. Hold on. Not with what Shane said though about it being under the threshold of being able to differentiate. You wouldn't do that. That's why I said he didn't respond to you. It didn't sound like it to me.
If I wanted to redo spherical excess data, right? If I found that below measurements of a mile, then there's no spherical excess. It only comes up flat. I would then outline my survey to do 100 measurements of not over a mile, and then proclaim that the Earth is flat. You see the flaw in that design, right? Right, Deza?
Oh, yeah, obviously when you do very short distances, there's going to be different effects. But
Right, well, then there you go. That's the whole point, bro. Thank you.
But so you need to get a range of measurements and see what happens over the range, and you'll get like some error bars that'll appear. That short, indistinguishable as the distance increases or as the angle drops. you'll get some kind of relationship between distance, angle, and your result. And that's what you need to see.
That's how our 28 other measurements all show the same thing without any one supporting sphericity. That's how we know.
They're more or less
That's
from
how,
the same place, right?
that's how we know there's even a
Similar kind of-
threshold, right?
Same
They're all
place at
taken from
different
high
distances.
altitude with similar scenarios, right? So you need a whole bunch at sea level and a whole bunch at different places, just to get a variety of environmental configurations that might impact what's going on.
But you wouldn't do any of that. Would it be under the threshold of you being able to differentiate between any model? You just wouldn't do that. The thing James said that you didn't respond to.
No, you would, and that'd be part of your analysis, right? So you'd see that, when we're very short distances or very steep angles, we cannot distinguish between the two models here. That the direct geometric representation is predicted on the Earth and on flat Earth and globe Earth, right? Because there's
It makes sense, right?
Yeah.
All right.
So what you need is all those ranges in between where you can distinguish.
Right. But so John's method specifically was to find one or two measurements below that threshold and then proclaim the whole process invalid. You understand that, right?
Yeah, but if his angle is the same, you'd expect the same.
Hold on, you just thoroughly understood the point when it wasn't John's, right?
No, yeah. But if the angle's really steep, there's going to be a whole bunch of scenarios. So you're going to get a whole bunch of variables that you need to work through, right? The overall length of the theodolite's importance, the angle.
Come on, man, really?
Dude, come on, stop obfuscating.
No. It is important to have a whole range of measurements, different angles, different distances, and then have a look at what the behavior is.
I'm gonna need you to say that John's method is retarded, Daz. I'm gonna need you to say it.
It's one sample. It doesn't prove anything one way or the other, but it's another sample in the data set that you need to
I'll give it a hard
the
R.
validity of this technique.
So his whole position is that this one measurement that he's concocted, with below the margin of threshold to be able to differentiate between models, that one measurement is so good that it debunks the whole model, right? That's why no one wanted to hear him talk about it for the third time.
I'm not saying it debunks the whole model.
Well, that's what his claim was, right? And that's why nobody cared. So I'm gonna need you to
He said
say
the method was invalid because of his 1 mile angle.
Yeah, right.
Which he literally admitted, saying, you can't tell the difference between flat and globe. Oh, thanks. How fucking useful. Not at all. Not at all useful. That was the point. You need enough distance to show the differentiation between globe prediction and flat Earth prediction. That would be a good analogy. If you had something like that was analogous, then yeah, we'd hear him out. But he's literally not making it analogous and trying to throw out the method altogether, which is weird. It's a weird move. Did you get that right, Daza?
Yeah, I understand where you're coming from. Yeah, that it's certainly, if you had high enough precision measurement, you might be able to say that that's a robust.
Yeah, but what's another way you can get around that? Oh, I know.
Right,
increase the distance.
Well, look, here's a bunch of measurements.
Change the elevation, right? Move to sea level. Do some observations from an observer at sea level, getting similar geometry. You could do that as well.
Here, in the same logical fashion, then here's some data from the spherical excess from the American arc of the parallel. Here's 3 measurements of flatness under 180 degrees. Therefore, all the 180 pages of so-called spherical excess are dumb, null and invalid. Right? Done, debunked. Now, can you say simultaneously that this is not retarded, but what John is saying is not retarded? Come on, somebody's retarded.
Everything's retarded.
Right, so here's the same principle. So now you better not argue spherical excess ever again, because here's measurements of flatness. So the whole method is obviously bunk, right? The method should be able to differentiate between models on every measurement, right, by the same logical framework.
Yeah, at least within some
newsflash for you. That arc of the parallel 900 whatever page document that doesn't have a single measurement of a single triangle. That's all averages with weighted mean averages. Like there's not a single one measurement. There's not one actual measurement. It's crazy.
Even that with corrections and excess tables and pre-corrections and adherence to models with no actual, journal data or whatever, it still came up to, below a certain distance threshold always came up flat, right? So they knew that beyond a certain distance that they would be able to measure or create sphericity in the corrections, however you want to interpret that.
Yeah, and that's kind of the standard thing that and I guess you're right with John's measurement, is that beyond the threshold. So you'd have to look at at precisely what was going on there in terms of is it below your ability to measure that angular difference because of the distance, and what is the threshold that we should be able to start to see the difference. So it's probably more valid to use longer distances, various angles, and change the elevation. For me, probably one of the key things is the elevation there, that you're doing some very high altitude. So It's going to be a little bit different.
Yeah, for John's method to be taken seriously, he would give me like one really short measurement and one really far measurement, right? And if they were both indistinguishable, maybe we'd have problems because you couldn't entertain either end of the extremes. I mean, that would be logically incoherent, right? So
yeah, so we need a whole bunch of other things that viable distances, I guess, to see what's going on.
Wrote a Google document on this one thing, and he's like, "Ta-da! Look, behold!" And then nobody wants to hear his bullshit, and he's like, "Look how threatening I am! Behold, sycophant!" Whatever he says to you guys.
Yeah, but for me, there are still a few key challenges. One is the physically observed angles. If you were to measure these angles of occlusion with a theodolite from both the observer location and from the occlusion location, we know that the angles that you would physically observe are not what are predicted without refraction. There's a gap there that we need to understand. And and a direct contradiction with other measurements we have of the shape of the Earth.
So what you're saying is that he's always guilty, this suspect, but you want to find ways to make him guilty by altering the footage after the fact? Yeah, that's kind of what you're saying, right? So my suspect is definitely guilty because you're playing criminal attorney offense for this guy. I guess all of a sudden, instead of picking is he guilty or not guilty, we're going to play criminal defense lawyer for the guilty guy, and we're going to try and make him not guilty because that's what all you Globers are doing super hard, right? So now you're like, okay, look, he was there, but it was an AI generated image of him. Okay, he definitely wasn't there in reality. The camera only shows him to be there at the exact position. Is that your argument?
No, it smells bad. Is my argument. It's got a smell about it that doesn't seem right. I don't know what it is, but it doesn't seem right.
No evidence.
So
Your Honor, I would like to declare a mistrial.
That's fair.
The reason I think it smells is because I have other measurements of the surface curvature.
Personal incredulity is not an argument.
Just start shouting reciprocal zenith angles if it makes you feel better, right? Like, but that's not going to refute this particular argument.
And you know my argument, Shane. I don't do optical stuff very well. I have a good handle on GPS, and that is my baseline for what the shape of the Earth is.
Yeah, you're not alone, dude. A lot of people have come to that conclusion, especially people in the field, like our boy Eric, who worked with GPS and satellites quite a bit and helped us learn. He definitely, I think, maybe still is a globularist. We don't really press him on it, but fully believing because with the model he was presented to do all of his work, being spherical and long lat being a coordinate system that like works, you can find everywhere, right? You can locate on it. He has never had any question to question. I think that's
the cool thing, right? So once again, I don't want to divert down the GPS path, but GPS doesn't require lat long establishing a point of surface on the Earth, right? You can establish that location without lat long. You have a geometrical measurement of your position relative to all of the transmission sites, right? And you establish a set of geometric coordinates. Geometry isn't able to be transformed by a coordinate transformation. That is fixed. And that's what you get with GPS measurements is a geometric position.
Well, with the z coordinate for height separated from anything, you need a level, you need a zero, you need a ground datum, and that datum comes from the spherical datum. That's how the ECF.
Come on, Shane, you can do better than that. The z coordinate in GPS is not. So we have 3 vertical planes in GPS, right, as our coordinate system. Z coordinate is not relative to the surface of the Earth.
Whichever one it is. Whichever one is relative to the surface of the Earth is relative to which surface. How do they determine it? Of course, there's a height component, right?
Now that's after. So your initial position is calculated relative to these 3 orthogonal vertical planes. And you get a 3-dimensional coordinate there. Then if you want to work out lat long, you've got to then take the globe model and work out where that position is on the surface of the globe. You can, I think they actually did this. So you derive the globe model from GPS measurements and you're able to establish what the spheroid is in ECF coordinates. And then you can say, right, here's the spheroid. Let's transform our ECEF to lat long based on that spheroid that we've measured independently in ECEF.
You say measured, but we're saying it comes pre-corrected with that model dictated as the level from which to measure the height, right? And we have backup for that with Wolf and Pettit when they first went into that for the Sagnat corrections, when they first found the pre-corrected data for meridian corrections, when they were trying to converse the same coordinate system. So like what we say is uncorrected ECEF raw is actually pre-adjusted to a surface level, which becomes a geoid.
Can you precisely explain those corrections to me? Because as a user of GPS, when you get your signal and its timing, there is no correction you need to apply that is dependent on the shape of the Earth to get a position. You can do it without any corrections at all, if you like, and still determine the shape of the Earth. And the corrections have to be for everybody. If there's a correction to the timing information in GPS, it has to be for every receiver.
We'll have to go read Wolf and Pettit again because it was particular to the
They weren't clear about the data they got from what I saw. That they got some data from GPS. It wasn't from directly from the satellite. I think they got ground station data. Ground station data had some pre-processing done to it that they weren't expecting. But as an end user, you're not worried about the ground station. All you're worried about is the signal that you receive. And everybody receives the same signal, has the same information. All that varies is the time it takes to get to you. And that signal has to be coherent across every single user of that system. Otherwise, you will not be able to get coherent locations between two places. And it's quite easy to demonstrate that GPS measures good geometry because you get an RTK system or a long duration survey grade measurement like they do when they resurvey the NAVD benchmarks. They plonk the GPS on the point for 8 or 16 hours and they collect enough data to get down to sub-centimetre precision. And that level of precision lets you measure geometry very precisely.
Okay, Dazo. Well, it's pretty corrected. So to do C plus V with respect to ground, I mean, it doesn't matter.
That's the Sagnac-like effect, right? And if you don't apply it, Shane, it doesn't work, right? So, and they only apply it in the component of the velocity that is in the direction of the rotation of the Earth.
So what GPS data do you have that shows the shape of the Earth that doesn't assume a geoid, ground-based position or something like that?
Yeah,
like which one is not on geoid?
So when you get your raw position in GPS Taylor, it's in a Cartesian coordinate reference system, which is not dependent on the geoid other than for its origin. It shares an origin in common with the geoid. It's only when you convert it to lat long and elevation that you are positioning that point in space relative to the geoid.
Are you saying so when they receive information from these transmitters, like it's taking a longer distance for one point versus the other, which would imply curvature?
No, it doesn't imply curvature. So the curvature is... So if you imagine you have recorded your GPS track across an ocean, right? And at every point that you've recorded, you get a three-dimensional coordinate, an XYZ coordinate. If you plot those coordinates on a graph, they fit the surface of a sphere, right? And that sphere is also the geoid.
How would they fit a sphere versus a flat plane?
So, well, it's geometrically, each position you get is geometric in space, a 3D XYZ geometric position. And those positions fit a sphere, they do not fit a plane.
Because the timing difference or what?
The timing difference is what is used to calculate your position. So imagine you've got 4 GPS satellites and you're connected to them by a piece of string. And you pull the string tight, and that defines your position. So you know where the length of the string is, you know where the satellites are, you can work out your position compared to the satellites. And you move somewhere else, go through the same exercise, you work out where you are compared to the satellites, and that's your geometrical position relative to the satellites, each of those points. And as you collect those points across the surface of the Earth, they form a sphere. So your position relative to the satellites makes out a track that is spherical.
How would it know it's not just at a further distance rather than the timing difference is because it's drop over distance?
So the distance you calculate is based on timing. The key thing is that distances that you measure between receivers also have to be coherent. Otherwise, if you try to measure the distance along the ground using GPS, it's not going to work unless everybody in every location is getting a coherent position.
I'm just wondering how the timing difference coordinates the curvature rather than a further location.
So the timing difference between signal receptions gives you a different location in 3D space. So as you get further away from a receiver, from a transmitter, the distance gets longer, right? The timing gets longer, so your distance is further. And as you move around and you establish your position because of all these timing differences, you get a point in space. And those points in space are what give you the curvature.
But don't the transmitters tell the receiver the location, and wouldn't that location that the transmitter is at already be incorporated into the geo model?
No. So the satellites broadcast two things primarily. They broadcast an ephemeris and time. So you can work out at any point in time where they are in a particular coordinate system. And you use that position and the time the signal arrived at you to work out how far away. It's not dependent on the geoid. Those positions of the satellites aren't dependent on the geoid in any way, other than the center of their orbit is also the center of the geoid.
But you just said a particular coordinate system. So wouldn't that imply
Yes.
assuming curvature from the get-go?
No. So the coordinate system is one in free space. You can use they actually use GPS on the moon as part of the Firefly mission a couple of months ago. They managed to get GPS lock and locations in orbit around the moon and on the surface of the moon. And so GPS, doesn't matter where you are, if you can get signals, you can work out where you are compared to all of the satellites that you are looking at.
Yeah, I guess like The only thing I don't understand is how they would know that the distance away would be because of drop over distance or because of a further distance, like left to right. I don't know, like how to differentiate that.
It's just a geometrical straight line. So the process is trilateration or multilateration. You have the locations of the satellites and the distances to them all, and that gives you a point in space relative to the satellites, not relative to anything else, just relative to the satellites.
So if I'm on the moon, you'll know where I'm at, but what time zone am I using?
I don't know. You could pick any time zone you'd like to learn.
I'll answer my question. They had released the lunar time, I think it's the lunar time zone, or whatever it is. And it's funny how they do that a year later, then all of a sudden they have GPS on the moon.
I don't quite draw the correlation there, but anyway.
So
from
what I'm seeing, the elevation provided by GPS is initially an ellipsoid height, also called a geodetic height. Is that correct?
So GPS elevations are calculated like this. You get your point in space relative to the GPS constellation in an XYZ three-dimensional coordinate. Then to work out your elevation, you work out where you are above the geoid. So there's a model of the geoid. You work out your lat long on the geoid and the geoid height. And you draw a line up through to your point, and that's your elevation above the geoid.
But this is the problem, is that it's assuming geoid.
Only when you do lat long elevation, right?
Apparently all GPS does that. Which ones don't?
Lat long elevation is the second coordinate that is returned. The first coordinate is ECEF Cartesian coordinates. It is not dependent on the geoid. And that is converted to a geoid relative coordinate. So you can actually measure the properties of the geoid using ECEF. You don't actually have to use lat long elevation if you don't want to, but it makes sense because that's what people understand.
Yeah, so I'm just reading, sorry. The Z value of the ECEF is not directly a height above sea level or even above the ellipsoid. It's a coordinate relative to Earth's center. Height, ellipsoid, or orthometric is calculated separately. So the Cartesian conversion are necessary for accurate elevation measurements. So do you have to convert the Cartesian numbers after you receive them to interpret them?
Yeah. So you get so imagine you've got the Earth embedded in a big grid, a three-dimensional grid. Your point is one point on that grid, and it also corresponds to a point on the Earth. So you convert, and all of those points on the Earth are known by lat long and elevation. So you find out where your point in the grid is on Earth, and you work out your elevation above the geoid for your point.
Sorry, I was just at a gas station. Yeah, I'm definitely gonna look into that. If you have any data using like non-converted data, that shows, globe or whatever, I'd love to check that out.
I think Walter Bislin has a good website where he's got a whole bunch of tracks that they recorded, a whole bunch of GPS locations from the Vendée Globe race. They collected all the data there and have got the ECF coordinates of their racetrack. There's lots of data out there.
So in that data, do they mention like their materials and methods to how they got their conclusion? Because if that's the case, then that would be something to reference, like the materials and methods of how they did it.
Yes. So in the case of the Vendée Globe stuff, they just took the raw or took the GPS reported locations and displayed them. They have a number of exercises where they use survey grade GPS equipment to directly record ECEF. I'm not sure in Vendée Globe whether they actually had access to the ECEF initial coordinates or not, but I'll have to check that. In any case, a GPS coordinate, whether it's in lat long elevation or ECEF, you can translate between one and the other. They're equivalent. So a GPS lat long elevation is directly translatable to an ECEF coordinate. You'd prefer to see them before they are translated, obviously, in this case.
Yeah, so just by me searching it, I see like the ECEF, the Earth-centered Earth fixed coordinate system, assumes a reference ellipsoid. Is that incorrect?
It says assumes a reference ellipsoid. What's the context there? I wonder.
The ECEF uses a Cartesian coordinate XYZ to represent positions relative to the center of the reference ellipsoid, which is typically defined as the geodetic data such as WG-S84.
Yeah. So the only point, the only reference to the ellipsoid that the ECEF coordinates have is the origin. The coordinate system is common with the origin of the geoid.
Okay. This is obviously just like the crux of the issue is that if it's already like even the raw data is assuming ellipsoid, then what are we supposed to make of it?
Well, it's not assuming an ellipsoid. It's so in the case of the satellites, their orbital path is naturally around the center of mass of the Earth, which is the origin of the coordinate system of the geoid as well. So, yeah, and one of the things that you'll need to work out for yourself is, are the satellites where they say they are, doing what they say they're doing? And the way I determine that is that if they are not, firstly, your position won't be correct on the Earth, that you won't be able to establish your position if the satellites aren't where they say they are. And secondly, if you have two receivers, say 1 kilometre apart, and you're able to establish the distance between those two receivers, if your GPS positions aren't also 1 kilometre apart, then the whole thing is kind of breaking down if the satellites aren't where they claim they are. If you've got an Android phone, there's a tool called Android GNSS Logger. You can actually collect the GPS signal information, so the timing and phase information and navigation messages. You can collect it all and process it offline and work out where you were, and you can see the process of calculating your location. And you can do it for 2 receivers. You'll see that you'll have a big overlap in the information, just the timing will be different.
I guess the issue is like, does the ECEF assume ellipsoid? And from what I'm seeing, I mean, it said yes, but I'm like reading these, I'm looking at like all these sources and double checking.
Yeah. So it assumes that the center of the ellipsoid is the center of the mass of Earth, and that the satellites orbit the center of mass of Earth. The actual shape of the ellipsoid is not important in ECF, just where it is centered.
So X, Y, and Z, basically, does that assume curvature?
No.
No. Okay, well, that's the crux of the issue. All right, well, if you have whatever data you want to share that, goes through it, and so I can really go into detail with each of these points and look at their methods, then that'd be great. Because right now I'm just kind of driving and I'm in a store at the moment. But this is very interesting. Thank you for sharing.